Good day. This is a continuation of computer-aided design class where we started to design lubricant blender for Khazar University, and as you see, this is the place where we left last time. And I think we will continue by doing the top part of it. And yeah, so for the top part, I think we will do it like this, and yeah, we will do a new part here on this surface. We'll do a 4 millimeter plate, sheet plate, and this sheet plate will be consisting of two parts since it will be welded. So we add a new component, new part, and yeah, we do it directly here. So on this surface, and select the plane. Yeah, we have to select the plane. The plane will be this one. Let's select the plane from here. This, we need top plane. Okay, we selected the plane. Now we can do the part. And we go to sketch, we draw we do the geometry. Its diameter will be 2600, and it will be half because you can't make it whole because you don't have such sheet metal. You have to weld the sheet metal. So we just do the follow. Oh, yes, we delete this, that. So this is our geometry. We do is we extrude it now 4 millimeters, but with offset. So our offset will be, I guess, 2500 or even more. It's even more than that. It's something like, yeah, I see it. So 2650, 2655, exactly 2655. So this is the half of the top cap, and what we need now is to know how we're gonna connect this part. And my point of view is, let's to finish this cap thing. So we did this part, we call it the same names as the other parts. Just take their names from the folder. There's that folder. Let me find lubricant blender. So we have four parts. This is the fifth. We call it fifth part, and that's it. That's the fifth part. What we do is very simple. We close this. We save it externally, and after that we go for the lubricant folder. We go to this part, we open it, and we save it as the sixth part, the other part. And after we save that sixth part, we just do one simple alteration, which will be drawing the circle here, like this, deleting this part and finishing this. That's it. So we save it, we leave it, we open assembly again. We insert the part here, insert the components, we name it the sixth component, and we press OK. It should be already there, but it failed to go there. So we delete it again, we insert it. Let's see if it will get there or not. No, it doesn't want to get there. So we have to do some operations, like let's look. So we have to do, let me look, we have to do X operation. What now? No. Y operation didn't help. Z operation, Z, X, Y, Z, it doesn't help. We perform it again, and yeah, this time I'm gonna do X operation and put it like this. After that I'm gonna do mate function. I will make this part with this part. No, it went wrong with this. Look, it's not what I expected. I made it with this. Yeah, that would be perfect. But it doesn't work, so it doesn't wanna work. So what I'm gonna do, I'm gonna do concentric like this. Yes, and after that I will just do this surface with this surface, and I think that's it. The last thing would be connecting this surface with this surface. This is a third constraint, and that's it. We are done. So this is the cap. The things that left to be performed now are to do the entrance, to do the entrance part, and to put the things on it. Before doing the entrance part, I would gladly install the channels we have chosen to put on it. So channels I will install this way. I will do them as from the toolbox. So we have a toolbox which we can use for not drawing standard materials. In our toolbox we have variety of stuff. We'll go to Dean because I've studied Germany masters and I like German engineering, German technology, German products. Everything German is good, Japanese good, and Azerbaijani is also sometimes good. So structural members, steel, and U channel or UPN channel. We will use, I think, UPN channel. Yeah, let's bring it here, put it like this, and we will use UPN 200, like 200 millimeter one, with length of 2700 millimeters. Yeah, so we just insert them on this surface. Okay, let's insert them like this for now. And yeah, we need just two of them. And as you remember, I showed you their faces should look to each other. The outward should be So we just do mating here. So let me look at it. Yeah, we do mate this with that. It doesn't work because I think it's fixed. Yeah, no, it's not fixed. Maybe it has a mate. Let's look at it. Yeah, it has a mate. We delete this mate and we generate our own mate, which will be something like this. And after that, we do the following. We rotate it by 90 degrees and we do it like that. This line and perpendicular. So yes, we did it. What we do now is very simple. We move it here, and let me tell you, the distance between these two has to be, I guess, 200 millimeters, but I have to look to the book. In this part of design, we go to the book and look at the beam mounting, and in beam mounting we see that its distance between the ends of it should be at least 15% of tank diameter, and as you see the faces have to be looking outwards. So 15% of 2500 by it's like 400 millimeters, so it should be 400 millimeters away from each other. We just do the following: we continue to mate them with each other this way, and we put 400 millimeter distance, but it's distance between the this section. We need the 400 millimeter in by this part, so it's 400 minus 160, it's 340. Oh, it's too much or not? 340, I think it's normal. Let's look at this distance. It's, how long is it? It's 75 millimeters, so 360 is enough, and we also have to mate it here as well. So we mate it with this. So mating is crucial in order to have a normal geometry, normal assembly. We mate everything, and we also need to give this distance between this and the channel. Oops, it went the other direction. We don't want it to happen. We just do the following: we look at it like this and move it. So let's accept it as the middle of it, the center of the circle. However, we need to make a hole here, a hole by which we can install the mixer. So that hole will help us to dimensionalize the other stuff. So I have already did some calculations for the mixer shaft, and it's gonna be something like 80 millimeters of diameter for shaft, but we are going to install a bearing casing here, so the bearing casing diameter would be 500 millimeters. So 532 millimeter of the hole. Well, it looks too much to me. Let's because we have a 300 millimeter distance between them, so 300 millimeter would be good, but we have to check if the bearing will be able to perform this. So bearing 6216, its diameter, we have to get the data of its diameter. So let's have a look. Bearing diameter is 140 plus 50 millimeters to 100. This is totally fine. So 200 is enough for us. We make a hole. Save it. It's a great help for us because we needed this hole to make it axis-centric, so we choose this point and we give distance. So it's 100 plus 160, so 160 minus 100, it's 60. That's it. Now it's settled, as you see. All we need is to give another distance, which is between this and this, which is 2700 divided by 2, and that perfectly finishes the job for us, as you see. So all is left is to make the other parts, so we do the hole here as well. Wait, yeah, so we do another hole, and it's also 200 millimeters. We extrude it. That's it. So after doing this, all we have to do is to finish the casing. So let's draw the motor mount system, the system that which will hold the motor. So I guess it will be something like this. Actually, we have the book where it's already shown how to do it, so it's very useful for us. So I'm going to do it like this. It will be a sheet plate, but let's create a new part, and we do it on this surface, and yeah, it is something like this. So dimensions, so these dimensions 490. Well, it had to be 400. Something went wrong, so we have to fix this issue before continuing further, and that thing we can do easily by calculating. So it's 70% 150. We go to this one and we go to its mates, and yeah, the distance between these two has to be not 340 but 250. And yes, after that there is another mate here, which is this one, and for this mate we have to do not 60 but 25, I guess, and I'm excellently right. That's the numbers we have to give, and apart from it, I think that's pretty much. We go here, we check it, so it's 400. Yeah, that's it, we corrected our mistake. And the point is, I have to tell you that we have, if you see, there is a weld line here. We didn't put it the ribs, these channels parallel to it. We put them like perpendicular to it, because when you put it like that, it gives more rigidity to the structure. If you put it parallel to weld, it will not be that much efficient structure. And yes, we do the next. Our next steps would be, okay, this would be making a square like here, 200 and 200 again. Oh, it went a little bit too much. No problem. Now we extrude it 35 millimeters. Oh wait, did I do it 35? No, I guess it's 25. Yeah, it's 25. And it's pretty good. It's 25. We need to make some holes on it in order to connect it to the channels. We do not weld it to the channels because we want it to be mountable. So we can mount the mixer unit, and we can unmount it. So that's the way we put the holes on it. And as you know, the holes have to be, so if you're using bolt M16, your hole have to be at least 18 millimeters. So you give 2 millimeter tolerance for the production side in order to be able to mount it. There are even some cases where they do holes like this. So they do it like this. So it's even much more easier to mount. So some so it eases the production procedure. Of course, there are some projects where we have to use like 16 millimeter or 17 millimeter. It's closed fit, so there are types of fits. So the metric bolt fits. Let me show you it shortly. Metric bolt hole fits. Let me show you bolt diameter 12. Yeah, as you see, 10. No, that's not the one. Clearance. Yeah, that's what we need. So M5. So it's first class, the normal. If it's F5, you can use 5.5 millimeter. It's like loose, you can use 5.8. For instance, if it's M10, it's 11 millimeters for normal drill. It's 10.5 for fit class, fitting the hole. It's 12 millimeters for loose. So in production, it's strongly suggested in such massive structures to use loose fit, because loose fit allows the assembling guys to fitted properly. So 18 millimeters, and I just position it the proper way. You have to know that the holes have to be positioned properly, and this there are some guidelines for this. Oh, nice calculator. So you have to Google them. Let's say bolt hole formulas. Yeah, let's look what we get. They designing using the right keywords while searching is very important. So this is the key to successful design, because you cannot know everything, but you can find everything in internet and apply. You have to look at the data and gather the required information for your work, and you should be able to understand if it's right or wrong. Let's calculate M12 loose, take drill 14.5. Okay, it's a little bit too much, but let's look at M10. M10, 12. I think it's pretty good. Yeah, this calculator is working right because it's according to ASME standard. So this tool you can use. So let's look. Diameter 2, hole diameter 1, 8. Let's compute. Oh, 5. Interesting, but it's no use to us. Think, gives the coordinates. Good one, but useless for us. We were looking for something much more different. I think there's no need for that at this moment. We'll just take this distance as the middle of this channel. Channel is 75, so 35 is okay. 40, it's like this 35, this 40 is also okay. We just make linear this hole. In direction would be this one. We don't want in X direction, we want in Y direction. We'll reduce in X, so it will be at least, at least you should have at least 3 diameters away. So its diameter is 16, 16 by 54, so 70 millimeters, 80 millimeters is good. We do it 5 times, I guess it looks fine. 75, okay, 78, something like this. 5 bolts with diameter of 18. It's over 18. We can make it 18.5, so guys, don't get that much trouble with it. We just need to calculate distances between this, and we have to look what we get at the other end as well, and we get 48. It has to be fixed, so let's do it. 79, it's 44, and 80, it's 40. That's it, that's perfect. Now we just make a center line here, and we just mirror entities, and we get the holes on the other side. We make them whole, as you see. That's it for this part. The other things I would do here is make the hole for the pipe, and yeah, let's do it as well. We have time, I think. Oh, let's start. So we install bearing here as well, two bearings, and on top of it we will put a mount for motor mount. So let me look at it. It's so perfect. Okay, let's do the bearing seating. So sketch, and the bearing outer diameter is 140, as you know, and we know that the bearings B, the width is 26 millimeters. However, there's one little point to make. The little point is that, as you see, we want to use this cap, and this cap has some insert inside the bearing. You can use this one type as well, but I assure you this one looks much more better than that. And we look at C. We also have H. Yeah, we need this H. So you go to 140, the diameter. 140 is this diameter D here. So 140 has H value of 80 millimeters, as you see. So from it we know that to this value 26 we have to add 8, it will be 34 millimeters. So we just do the following. We have drawn it. Now we have to wait a minute, it's not a part sketch, we have to make it part sketch. Then we have to do the sketch on it, 140. So we make the drawings 140. We extrude it by 34 millimeters. That's the place where the bearing will sit. You should put radiuses here as well, but we'll do it later on. I perform the same operation at the bottom of it. So sketch. No, I want to sketch again. In sketch, yes. So I'm gonna do another one, 140. That's it. We extruded by 34 millimeters. That's perfectly fine. And all is left is to make these holes here, holes for the cap. You see this hole, so we make those holes like the one here, D1 or D2, I don't know. That I will use, wait a minute, D1, D2, which one? Yeah, let's go to 140, D1, D2, 11, 18, 24. Okay, it's, wait, they're so light. Interesting, why are they so light? Their weights are 2 kilos. Very interesting. Okay, let's look at it. So all dimensions are here. You just take these dimensions from this line 140 and insert there. That's all you have to do. You have to be careful, and that way you draw the cap, you draw the bolt circle, the number of holes here. It's also give the end the number of holes, and D is the hole diameter. So if you go to 140, you go for N, it's 6, so there must be 6 holes, and D is the hole diameter, so it's 11 millimeters, which M10 will be used. So we go here and we can do it, but we will do it for the bottom part. The bottom part, we just make a sketch and we draw a bolt circle here, and we can have a look at the bolt circle diameter as D1. It's 140 D1. Wait a second. Yeah, D1 140, so it's 160 for us. It's 160. So this is our bolt circle for construction. We make our holes. There are 6 holes, each of them is 11 millimeters. 11, and yeah, it's 11 for cap, but for the cap where connected it's 10. It's actually M10. It's the threaded hole where we will place the bolt, and we will have 6 of them in a circular way. And yeah, so when it's 6 and we want to do this one, but around this point, that's it, we extrude it by, let's say, 50 millimeters, and that's the place where you will insert your threaded bolts. It looks pretty good, but the top part, it will be much more different, because top part will hold the motor mount. So top parts we'll do later. Let's have a look at the whole design. At this point we have almost covered most of it, and the things that left are to finish the top part and to finish the legs of the geometry. Let's put the hole on it. So edit part, we put the hole, it's around 200 millimeters, as you know. So let's make it 190 or 195. Perfect. Make a extrude cut, and in this case we will do it like this. This is 195, and also we make another hole which is 200. Wait, so it's 200, and it's extruded just 10 millimeters. So point is, wait, is it extruded? Oh, I want to extrude it. Yeah, that's the point. So point is when you put this the bearing, the shaft on it, it will not move to the right or left or back and forth, because it will be fitted like this, and these walls will keep it from moving. And I'm gonna draw the with it itself. And yes, I'm gonna install a new part like this on this surface, and yeah, I'm gonna do that pipe. So as you know, the bearing, the S-curve bearing, the outside diameter is 140, so we should have at least 130, 100, I don't know, like 120, yeah, 120. Let me look. So 140 is this, D2, we should look at D2 is 126 millimeters, so it should be at least 120, so you can put the bearing on it. So I'm doing it, and it's something like this with inside diameter 100. Oh, sorry. So inside diameter 120, outside diameter 200. Let's say 200, 210, yeah, something like this. We extrude it. Let me have a look. We extrude it like 300 millimeters above, and we also extrude it downwards, but with other dimensions than that. So it's again this and 100, 200 millimeters downward, 10 millimeters, and after that we extrude it again downwards with 100, 100, it was 190, 90 by, let's, it's okay, SolidWorks, you can do it 400 millimeters, and let's look at it. 400 may be too much. I think that 300 is enough, but 400, yeah, let's leave it 400. That's it. So that's the shape we need, and yeah, that's the shape we need. So we will install bearing here, and we will install bearing, let me show you where. I think it would be fun to add bearings, but before doing that I want to make some modifications to geometry. As you see, the outer diameter is too much. Let's say it's 140, this is 190. I think that it it could be less than that. It's over designed. So it's 160, so this one should 160, 180, yeah. So 180 is more than enough. What we will do is we will change the dimensions, we will reduce them. So we go here, we take this and we make it 180. Then we go to this one, make it 190, and the other one has to be also changed, and it should be 200, I think. Yeah, some minor changes, and as you see, we have to change this one as well. We have to change this diameter. Let me look. Yeah, it's 195. Well, it will be 185. Is it right? Let's check it. Let's do some check with it like this. Yes, and we look at it. It seems not right. It seems wrong. Yeah, we need to make it different. Okay, we just go in it, edit, and here we go in it. We make it 180. The other one we make, let me find it. Yeah, this one is okay. The other one, find it as well. Yeah, the other one we make 190. Yeah, so this one is 190, and that's it. So this is it. We have reduced some material, and the point here is we make such a geometry so it doesn't create any issues like this motor mount falling down into the tank. It also doesn't create any issues like because of vibration it's moving right or left. As you see, it's properly linked here. It is not able to be vibrating. It's called classical approach over designed. And now I want to put the bearings on it. I'm gonna do it my way, so I'm gonna download the CAD. So I want a SolidWorks picture. I'll take, no, I don't need 2D, I need new tool or native 3D. Yeah? So it will be SolidWorks 2006. Download. That's it. Let's see. Yes, it's here. So we go for it, and we go to our folder. Where's our folder? We go to our folder, we put them there like this, and the next step will be very easy. We just insert the component, which is the assembly. Just one little thing I forgot is to turn on, okay, turn off this section view. I think it's time to save what we have done so far. It would be this one. Yeah, we need to put the names of it. So it will be something like this. So 7, 8, and we save it like this. Externally, as you see. Then we are free to do the next step, which is inserting the bearings. Yeah, so we choose it, we bring it here, we look at the surface. It's okay, I'll do it like this one. I will do the other one as well. 2, and then I will do the mate. operation. This with this surface, perfect. And I also want this with this surface. That's the boy. So this is this bearing. I'm gonna do the other one as well, but for that I need a section view, which is this. Perfectly done. I made it now. This with this. Great. And this with this. That's it. So these are my bearings. As you see, there are two of them. You know, the bearings, the outer cylinder is connected, is held by this system, but inner cylinder is connected directly to the shaft, and that's the way it works. The shaft rotates, but this rotates, and outer cylinder is static. Yes, it's a great work. Now what would I do is I would draw the cap for the bottom bearing, just to show you how it's done. And yeah, I think drawing the cap would be a normal thing for now. I think I'm gonna do it. I'll do it now, but which way? That's a good question. I'm gonna do it like this plate, like wait. I'll do it front plane, yeah. Adding new part to the front plane. That's my plane, front plane. That's it. Now we have to do a sketch, the front plane. It will be something like this. So going again to the CAD file, look at it. I draw it instantly without any hesitation. Something like this. Look, yeah, it's a little bit long. Should be like that. Something like this. Oh, sorry. It should hit the bearing, and it should be something like this. So this is the cap, and yeah. Now the dimensions. So H1 is, let's look at H1. It's H1. Which H1? Big or small? Big H1. Big H1 is 23. So we put it 23 millimeters. So which means that you can make it from 25 millimeter metal sheet or sheet metal. And then we look at small h. It's small h is 8. So which means this dimension is 8. Exactly, it's 8. What else we have? We have this, that. We have D. D is D. D is the D. D is okay. We have also this small one. How much is it? They call D3. So for D3, this is the one 125. So we divide 125 by 2. So these are 125. So there's still blue lines. So if it's 8, L1, we need L1, small L1. L1 is 16. It's 16. I think this is pretty much it. We just need to correct this one, and that one I will correct very easily. I will look at 45-degree radius, C45, 45-degree radius. Okay, CCC, it's 1.6. Okay, something like this. It's features. I don't have it here. I do it here with 1.6. Sketch fillet 1.6 millimeters. Like this, but it's too small. Maybe 1.6 is too small. We have radius here, small r. Let's look at the radius. It's 0.6. If I do the radius, okay, I got it. So we make a radius here. It will be 1.2 diameter, and from that we are drawing this line here, and we do the next step, and we make fillet 1.6, so it's 95 degrees, and it's 1.6 millimeters on each side. And yes, we delete this. That's it, I guess. Let's look. Yeah, perfectly. C by 45. C is 1.6. I think that's perfect. We just go to features, revolve base. We revolve it around this. Our geometry is this. Let's delete that. The axis of revolution is this. What's wrong? Something went wrong. Forgot. I have to make some cleaning here, like this. And I also need to finish this part as well. I need to add this radius here as well, and that radius, I don't know how much. I will find it here. Yeah, it's no. How I find this radius? It's not given. For not given radiuses, always we should use something, and I think I will use 2 millimeters. Let's do it. Fillet 2 millimeters. That's it. And now we revolve it. We should revolve this geometry around this axis. Still it doesn't want to do it. What's the problem? Some geometry creates a problem, and I see which one it is. Yeah, fortunately we have to make it tangent so it doesn't create issues for us, and we should give it a length 1.6. that way it's properly designed properly. defined, let's say, and we just give it to rotate like this, and this is it for us. Just make a look. This is the ghost cap, which will keep the bearing properly. All is left is to put some holes on it for the bolts. I think I'm gonna stop here for today. Next classes we will perform the CAD work on A4 paper, because I think it's the proper way for everyone to be able to perform it. Yes.